Good morning. Today we will start module 3. In this module, we will talk about instance based learning, and then we will talk about feature selection. We will show how in instance based learning feature dimensionality is a problem, and having many features is a problem for many other learning algorithms, and we will look for methods for feature selection. In the first part of the lecture, which we will have today, we will talk about instance based learning and specifically the k nearest neighbor algorithm. So, what we have is that, suppose in machine learning, in supervised learning, you have got training examples x, y, a set of them x I, y I, or you can say x I, f x I. So, these examples are given to you, and given these examples, you want to come up with a function f. You want to find an estimate for the function f. In the previous module, we have seen how to learn linear regression, a linear function f, or a decision tree, a function which is a decision tree, to estimate this f. Today, we will look at another setting called instance based learning, which is also called lazy learning. I mean, the algorithm that we will discuss is a lazy algorithm. We will tell what it means. Instance based learning, what we do is that when we get the training examples, we do not process them and learn a model. Instead, we just store the examples. When we need to classify an instance, that time we do something. So, we do not immediately learn a model. That is why the algorithm that we will discuss is also called a lazy algorithm. That is, the algorithm does not come up with a model a priori. Rather, when it gets the test instance, it uses the stored instances in memory in order to find the possible y. So, how does it do it? Suppose this is the instance space, and you have different points in the instance space. For each point, you have the corresponding x value and the y value. When you are given a new instance, you find what is the closest instance in terms of the x value, and suppose this is the closest instance, you find the y value of the instance and you guess the y value of this as the y value of this. This is the basic nearest neighbor algorithm. Now, in order to do this, given a test instance, you have to find similar instances. So, you want to find the most similar instance, or we will see in some cases we want to find some neighboring instances, the nearest instances. Now, how to find this similarity, or what is the distance function or the metric that we consider for similarity? We can use a standard metric like Euclidean distance, or other metrics like cosine and other, depending on the type of data that you are looking for. So, the basic k nearest neighbor algorithm, the algorithm that I am going to describe is called the k nearest neighbor algorithm. And let us outline that algorithm. So, the k nearest neighbor works as follows. As we have seen earlier, learning algorithms have two phases, training phase and testing phase, or the use phase. So, in the training phase, normally the model is learned. As I have said, for such lazy algorithms, we do not learn a model during training. So, in the training phase, we just save the training examples. We just save the examples. It is possible in a more advanced implementation to store the examples in some data structure so that searching through these examples become faster, but we will talk about that later. So, basically we just store the instances. Then at prediction time, so this is training time. So, at prediction time what we do is we get the test instance and find the k training examples. So, we get the test instance. For the test instance, we are given only the x value. So, we are given only xt and we have to predict the corresponding yt. So, what we do is that we find the training example x1 y1 that is closest to xt. So, among all the examples that we have stored in the training phase, given xt, we find that value of xi so that it is closest to xt. And then we predict yt as the output. So, we predict, sorry, not yt, y1 as the output yt. This is the basic one nearest neighbor algorithm. Now, in a more generalized form of the algorithm, instead of finding the single nearest neighbor, instead of finding the single example which is closest to the text example, what we do is that we find k training examples x1 y1 x2 y2 xk yk, which are closest to xt. So, k may be 3, 4, 5, etc. We find k nearest examples, nearest training examples, and predict as the output yt. What should we predict? It depends on whether we are doing a classification problem or a regression problem. For a classification problem, we look at y1, y2, yk, and we can predict that class which is the majority class among y1, y2, yk. We can predict the most frequent or the majority class. So, we predict the majority class from y1, y2, yk. But what if it is a regression problem? We have got different numerical outputs y1, y2, yk, and we will predict the average. Predict the average of y1 among y1, y2, yk. I find out the average and predict it as the estimate of yt. This is the basic k nearest neighbor algorithm, which is very simple. Now, let us just look at the one nearest neighbor. For one nearest neighbor, let us see, if you look at this slide here, these points are the different instances in the instance space, right. Now, depending on where your test point will be, if your test point is here, the closest point to this is this point, right. So, in this space, we have different points. The classification of a point in this space for one nearest neighbor is coming from the most nearby point. Therefore, you can think of, we can divide the space into regions. So, this blue region, this violet region, purple or whatever, the purple region corresponds to those places in space for which this is the nearest neighbor. This region is the region for which this is the nearest neighbor. So, we have divided the space into different regions, and this particular type of division or this structure, data structure is called a Voronoi diagram. In this Voronoi diagram, which can be constructed by, you take any two neighboring points and find a perpendicular bisector of the line joining the 2 points, that will give you a separation surface. So, like this you can draw the Voronoi diagram, and in this Voronoi diagram, in this region, this is the nearest point. For this region, all points in this region, this is the neighboring point. So, this captures the decision boundary of one nearest neighbor. And as we have seen, if you look at the slide, this is the basic K nearest neighbor classification, which we have already discussed. In the training time, a training method is to save the training examples. At prediction time, you find the K training examples that are closest to the test example X. For classification, you predict the most frequent class among those K yi values. For regression, you predict the average among the yi's. So, this is a very simple algorithm. So, what we will discuss are certain points related to this algorithm and how to improve the algorithm. Some of the issues that we will discuss is when we use K nearest neighbor, where K is greater than 1, is there a possibility of giving different weights to these K neighbors? So, we can weight different examples, maybe because of distance. Second issue is how to measure closeness. What type of distance function one can use? Today we will discuss that we can use Euclidean distance function as one of the metric, but other distance functions are possible. The third issue which is important, which we will discuss later, is how to find the closest points quickly at runtime. As we have seen in such lazy algorithms, during training time we do not learn a model. At prediction time we get a point and find the nearest instances. If we do not use a good data structure or a good method to store the examples, we have to go through all the training examples, find the distance and find the smallest of them. And if the training set is large, this may take considerable time. So, one issue of concern is to set up data structures so that this can be done efficiently, which we will not discuss today, but you will get some ideas in later classes. Okay. So, first we look at a standard distance function called the Euclidean distance function. In Euclidean distance function, what we do, suppose each instance X has n attributes, xi1, xi2, xin. Suppose we have n attributes, and between two instances xi and xj, xj1, xj2, xjn. So, given these two instances, we want to find how close they are. I think all of you know about the Euclidean distance. In Euclidean distance, how do we measure the distance between these points? We say that the distance Euclidean xi xj is given by root over x I k minus x j k whole square sigma k equal to 1 to n. So, this is the Euclidean distance. So, we can find the Euclidean distance from a test point to all the points that we have got from training and select that point which has the smallest Euclidean distance. When we take k as to be more than 1, we can take the, if it is a regression problem, we can take the average of the values. Now, when do we go for averaging with large k, or and when do we go for k equal to 1? So, we will go for averaging under circumstances where there are noise in attributes. So, because of the noise, the instance that is closest to the test instance may not capture everything about the test instance in a better way than another instance which is slightly further away, but still close. Then there can be noise in class labels. And thirdly, classes may be overlapping. So, under such circumstances, there is a case for using k larger than 1, and we will see that when we use a larger value of k, we get a better, a smoother classifier. Now, the second thing we will worry about is when we look at the Euclidean distance, we are taking the sum of squares, root over sum of squares of the distance for each attribute. Let us not use k here, because k is used for k nearest neighbor, but we are talking about an index variable. So, let us use m. Okay. Now, all attributes are not equally important, or the attributes may have different scales. So, a normal Euclidean distance treats all the attributes at the same scale, but there may be a case for giving different weights to the attribute. When you are giving equal weights to the attributes, you can give equal weights only under certain circumstances or certain assumptions. Should we give equal weights to all attributes? Now, if you can do so only if the scale of the attributes are similar. What do you mean by scale? Suppose height is an attribute. If you are measuring height in centimeter versus height in feet, the differences are not the same, right? So, you have to, the different attributes, depending on what scale you use it, it will contribute more value or less value to the distance. So, if you are giving equal weights, you are assuming that the scale of the attributes and the differences and are similar. What do you mean by differences? This xim minus xjm, how different they are for different pairs of training examples. If that is similar, then only you can use equal weights. Secondly, you make the assumption that you scale attributes so that they have equal range. If one of the attributes have values from 0 to 1000, another has values from 0 to 1, then their range is not the same. So, their ranges should be similar and the variance should be similar. Under such condition only, you can go for such a simple Euclidean distance function. Also, you are assuming that you are taking xim minus yim whole square. So, you are assuming that classes are spherical. So, the second assumption is that classes are spherical in shape. Right? Under these assumptions, you can use basic Euclidean distance. But what if the classes are not spherical? What if one attribute is more important than another attribute? What if some attributes have more noise than what you have in other attributes? Under those cases, this distance function will have some problems. And the way you can overcome these problems, there are several things that one can do. One is you use larger k to smooth out the differences, and you use weighted Euclidean, you use weighted distance function. Okay. Now, what we will do, now when you say you use larger k, you have to have some idea how large or small k impacts. I think before we try to look at that, let us look at some example. So, this picture taken from the book by Hasty, Tibshirani and Friedman shows an example where we have three classes, blue, red and green. They are denoted by the blue, red and green circles. So, if you use one nearest neighbor, you have decision boundaries between blue and green, green and red, red and blue, etc. Based on that, these lines show you the decision boundary between the classes. So, you see that this decision boundary is very, it's not at all smooth. So, what we can see is that if you have small value of k, so small value of k, it captures fine structures of the problem space better. You can see that these lines capture very fine structures of the problem space. For example, here you see in this region the class is blue, whereas in this region the class is red, right. So, in the small region here the class is blue, whereas these classes are red. So, the fine differences between the classes are captured when k is small. So, when small k captures fine structure of problem space better, if such fine structures exist. And this may be necessary if the training set is small. On the other hand, you can use large value of k under the following circumstances. Let us first look at an example on the same data set using 15 nearest neighbor. What you notice here is that the classes are more smooth. The neighboring classes, here all of them are classified as red rather than blue for 15 nearest neighbor. So, you use large k under these circumstances. So, when you use large k, the classifier that you get is less sensitive to noise. Particularly noise in the output class. So, particularly class noise. You get better probability estimates for discrete classes. And you can use for discrete classes. If the classes are discrete, you get better probability estimates if you use large values of k. Thirdly, if you have larger size of training set, then you can use large values of k. So, larger training set allows you to use larger k. If you have very small training set size, you cannot use large k, you have to use small k. So, this is the basic idea of getting different values of k. Now, let us look at the next diagram on the slide. So, this picture shows this shows the number, x axis is the number of neighbors. The blue line is test error, the green line is 10-fold cross validation error, and the red line is training error. And the dashed line is Bayes error, which is close to the true error. We see that in the training set, as we are increasing the value of k, the initially the error will increase and then error will after that remain almost steady. But for the test error and for the cross validation error, we see that for k equal to 1, for one nearest neighbor, the error is high and then the error falls off. After some time, the error rises and then keeps almost fixed. So, this is the region where the test error is smallest, and this is the region where the cross validation error is smallest. So, in this particular example, the error is smallest at around k equal to 5 or k equal to 7. So, where for small k the error is high, for large k also it increases, and some middle value of k you have the best performance if you look at the test error. Now, we come to the second question. The first issue was using different value of k. The second issue was to use weighted distance function. Now, we will see how we can use weighted distance function. In the case of weighted distance function, what we do is that we define the distance, let me write it in our notation, distance between xi and xj depends on, so we have different attributes with different weights. We have n attributes and their weights w1, w2, wn. So, we take sigma m equal to 1 to n, and then we use Wm into xim minus xjm whole square. So, this is weighted Euclidean distance. We are using different weights for different attributes. So, for those attributes which are more important for the particular classification, we can use larger weights, and for less important attributes, we can use smaller weights. These weights can also be decided based on, if an attribute has larger range, we can use small weights. If it has small range, we can use larger weights, or we can scale the attributes so that they have similar range, and we can sort of normalize the attributes so that they have same mean and same standard deviation. Based on that, we can then fix the weights depending on the importance of the attributes. And if an attribute does not matter, it is irrelevant, the attribute has 0 weight. So, this brings us to an important question, that if we have the instance space defined in terms of a large number of attributes or features, it poses a problem in defining an appropriate similarity metric, and it may also pose a problem for different other learning problems, because some features may be more important than others and some features may be irrelevant, and this specifically impacts k nearest neighbor or instance based learning algorithms greatly. So, it is important for us to remove extra features, because if you have a very high dimensional space, two items which are similar may still differ in some unimportant attributes, and the differences in distance between different pairs of items will be almost similar. So, it will be difficult to find good representative training examples for a given test example. So, feature reduction is very important. We will talk about feature reduction in a later class, maybe in the next class. But to summarize, in distance weighted k nearest neighbor, we have a trade off between small and large k, which can be difficult, because large k means more emphasis on nearer neighbors. So, in the weighted KNN, the prediction is based on this weighted average, right, and this weight can be based on the distance. The weight can be proportional to the inverse of the distance between the two examples. So, for a particular test example, suppose this is a test example. Suppose this is a test example, and these are 3 nearest neighbors. Now, this is closest, this is medium distance, this is a little further, right. Now, we look at the class of all these 3 instances and take a weighted average. We give larger weight to this, smaller to this, and smaller to this. Based on this, we can do the averaging. This is called distance weighted k nearest neighbor. We can also, instead of using this distance in the weight based on the inverse of the distance, we can use other types of functions for this weighting. So, one of the ideas is locally weighted averaging. What locally weighted averaging does is that, suppose k is the number of training points. So, instead of we could also take, instead of taking k as 3 or 4 or 5, we could take very large value of k. In fact, k could be entire training examples, and then we could give different weights to different training examples. So, if k is the total number of training points, we can define a weighting function so that the weight of nearby functions will be will have some reasonable values, but for further training points also some weight will be taken, but that weight function, it will fall off rapidly with distance. For example, you could think of the weighting function based on a Gaussian function. Right. So, this is very rough is still a Gaussian function. Suppose this is your test point. So, any example which is here, it will get this much of weight, an example here will get this much of weight, example here will get this much of weight, and examples further away will get almost 0 weight, but it will get some value of weight. So, we could use different weighting functions. For example, here we are saying Wk is 1 by e to the power kernel width into distance between Ck and Ct. So, we are using a exponential function, and the weight is falling off rapidly after, based on this kernel width. So, kernel width controls how much of the neighborhood you want to give reasonable weighting. So, if kernel width is large, you are considering more more area in the neighborhood. If it is small, you are using less area in the neighborhood. Based on that, you can do locally weighted averaging. With this, we come to a close for this today's lecture. In the next lecture, we will discuss issues about feature dimensionality reduction and other issues. Thank you very much.